Okay, so another predictive problem. This is just going to be, this is out of chapter 21. If you need a hint, you won't get that later, but we're going to take a chiral ester, we're going to treat it with LDA and then an aldehyde, and we're going to see what happens. So hit pause, go away and work this problem, and keep stereochemistry in mind. Okay, so you're back. I hope you kept stereochemistry in mind. This is going to be just essentially an aldol reaction. We're going to make an esterinolate, so it doesn't get called an aldol explicitly. But where are my pens? Okay, so we do have one enolizable atom here. So we have a very strong base, LDA. And remember, this curved arrow doesn't mean nitrogen from way far away throws its electrons. It means it actually has to encounter this. That's a pretty hindered proton, but this reaction works really well. We get an enolate. And we have on the side NH, you get diisopropylamine. So this is a lithium enolate, lithium plus. I'm not going to be showing the positive counterion to the enolate a whole lot. It is actually really important. The outcome of the reaction, the stereochemistry of the outcome of the reaction is dependent on solvent and counterion. But as an introduction, we're not going to get into all that. Diisopropylamine has a pK of about 34. pK of an alpha proton to an ester is about 23. So about like 13 orders of magnitude the enolate's favored. You can also note I've gotten rid of the stereochemistry here. So why is that? Well, draw a resonance structure of the enolate. Okay? That's no longer a chiral center. And the enolate, remember, the enolate form is the best descriptor of the actual structure. So even though you might have worked hard to make this chiral center optically pure, it's gone. And in fact, if you ever encounter a carbonyl that's got a chiral alpha carbon, you've got to be very careful with that, because if you expose it to base or acid, you can epimerize that chiral center. The other stereochemistry here, remember, we can also make E and Z enolates. Okay, so do priorities. So O is O and O. Crap, I've always done this with ketones. So what is this? This O is O and O tie, carbon versus minus. So this is going to be 1 and 2. CH2 beats methyl, so that's 1 and 2. So this is an E enolate, and this one's got to be Z then. And typically, so E and Z, like I said, I usually do this with ketones, and then in that case it works out. The O minus is the high priority group, the other group's bigger. So if you look at this, which one of these do you get mostly? You're mostly going to have the small group, in this case the O minus, on the same side or cis to the big group. So slightly favored here. This is kinetic. So it's 13 order of magnitude difference, so the LDA goes in, pulls the proton off, you get what you get. You're going to get a little more E enolate than you will Z. That's something to think about. As you do aldol reactions in this class, it's not going to be a huge issue. Okay, so let's back off all this right now. Again, you can rewind to see that. And I'm going to draw, just get rid of all of it. I am, for this reaction, going to draw this enolate as a negative carbon. Okay, again, those enolates I drew with the carbon-carbon double bond and the O minus, those are the best descriptors of the structure of the enolate. The best descriptor of the reactivity of the enolate is this one. All right, so this is the product of step 1. Step 2 then presents an electrophile. And I better, to keep the stereochemistry the same, I better keep it the same. Okay, so enolates aren't going to do anything with alkenes. That chiral center is not on an alpha carbon, it's on a beta carbon. There's no way to pull that proton off, so that one is going to stay secure. We can figure out what it is later. So the negative is going to come in and attack the carbonyl. So the negative carbon here attacks the carbonyl. And this is a reversible reaction, but it's going to stick this time. So let me draw, let's start with the that looks like I drew a wedge, sorry. All right, now we have 3 stereocenters in this molecule. All right, the alkene has no stereochemistry. We've got the chiral methyl from the aldehyde. We've got the chiral carbon that used to be the carbonyl carbon. And then we've got the chiral carbon that's nucleophilic. You're going to get a mix of diastereomers. And this is where, as I was saying, the counterion, the solvent, all that can affect your mixture of diastereomers. But this will be SNR, this will be SNR. This one is going to stay whatever it was, right? So this is step 2. There's no chemistry that takes place here, no arrows going to it, no atoms leaving it, so you leave that stereocenter alone. Step 3 is just to add proton in. The O- is going to take that. So we get an alcohol. You have to be a little careful in the workup here. If you use too strong an acid, or you leave it too long, or you heat it up, you can hydrolyze that the ester to the carboxylic acid. Okay, that's the product.